In the macrodroplet regime, the excitation spectrum of a strongly dipolar quantum gas is explored, focusing on the crossover from a Bose-Einstein condensate to a trapped macrodroplet. The dipole-dipole interaction plays a crucial role in shaping the spectrum, which is sensitive to the orientation of the dipoles with respect to the trap axis. For a dipolar Beck confined in a cigar-shaped harmonic trap, the spectrum of excitations develops a local minimum at finite momentum, known as a rodent, when the dipole orientation is perpendicular to the weak axis. The ratio EDD, controlling the rodent energy gap, is defined as the ratio of the dipolar and swave scattering lengths. Increasing EDD decreases the energy of the rodent mode until it softens, leading to the formation of supersolids and independent droplet states. In contrast, when the dipole moment is aligned along the weak axis, the DDI is attractive for small ky and becomes repulsive as ky increases, resulting in a macrodroplet state. Theoretical works have revealed remarkable features in the excitation spectrum of the macrodroplet state, including a stiffening of the spectrum at low ky and a multiband response to excitations, denoted as the antiroton effect. Experimental verification of these characteristics is achieved through Bragg spectroscopy over a wide range of momenta, confirming the predicted stiffening of excitation modes when approaching the macrodroplet regime. The successful production of degenerate quantum gases of magnetic lanthanide atoms enables the study of strongly dipolar BECs. The experimental results are in good agreement with numerical calculations taking into account finite size effects. The observed stiffening at low K and the spreading of the system's response over multiple bands indicate the heightened resilience of a dipolar macrodroplet against excitations. This increased stability could potentially lead to the self-evaporation of these excitations, introducing a novel aspect to the behavior of quantum systems bound by beyond-me-Anfield quantum fluctuations. The extension of the current theory to finite systems reveals the importance of finite size effects in the macrodroplet regime, providing a deeper understanding of the physics of strongly dipolar quantum gases and the behavior of macrodroplet states. The excitation spectrum of a dipolar quantum gas in an infinite tube is explored theoretically and experimentally, with a focus on the emergence of a novel excitation known as the antiroton. The dynamic structure factor, DSF, S, K, omega, is used to quantify the density response of the system to a density-coupled scattering probe of momentum Hc and energy h omega within linear response theory. A variational method is employed to determine the excitation spectrum, based on the plane wave ansatz for the excitations along the y direction of the infinite tube. This approach provides a semi-analytical expression of the dispersion relation for the lowest excitation branch, as shown in equation 2. The variational dispersion relation accurately describes the full excitation spectrum in the rodent regime, where dipoles are perpendicular to y, as evidenced by the remarkable agreement between the variational expression and full numerical calculations. However, in the macrodroplet regime, where dipoles are parallel to y, the variational method is only capable of describing the low momentum part of the dispersion relation, ky less than 1, L rho. For larger momenta, the variational dispersion relation deviates significantly from the numerical results. The full calculation of the DSF reveals a strong multibranch response of the system for ky1, L rho, indicating the emergence of new phenomena not captured by the variational method. These qualitative behaviors persist in the experimentally relevant case of a three-dimensional trapped system, albeit with expected broadening and discretization of the excitation modes. To probe these theoretical findings, a dipolar Beck of 166 Er is prepared in an elongated trap with the dipole moment aligned along the weak axis y. Bragg spectroscopy is employed to explore the spectrum of excitations of a macrodroplet state. The response of the system is measured as a function of the excitation frequency omega L, or for three different values of the imparted momentum kl. The experimental results are compared to theoretically calculated values of S0, ky, omega, which are rescaled in amplitude and account for the experimental Fourier and Doppler broadening. Experimental studies on the excitation spectrum of an elongated cloud polarized along the weakly confined axis have led to the observation of antiroton phenomena. Using Bragg spectroscopy, Researchers measured the momentum distribution of the atomic cloud after imparting momentum through photon absorption from a moving lattice. By varying the imparted momentum over a wide range, the resulting spectra revealed resonance positions, which were found to be in good agreement with numerical calculations, including Doppler and Fourier broadening effects. The observed spectrum of excitations exhibits a steep upward curvature of the first excitation branch at low momentum, with a decrease in slope and the emergence of a multiband response as momentum increases. The experimental findings confirm the presence of antiroton phenomena, which indicate the macrodroplet's resilience to excitations, and are supported by theoretical predictions. Notably, the study highlights the importance of considering both Doppler and Fourier broadening in interpreting experimental data, as these effects significantly impact observed resonance widths and the ability to distinguish separate excitation branches. This research demonstrates the potential of Bragg spectroscopy for probing the excitation spectrum of elongated atomic clouds, providing valuable insights into the behavior of macrodroplets in the context of quantum many-body physics. In the crossover regime from a Bose-Einstein condensate to a macrodroplet state, an experimental study of the excitation spectrum of a dipolar quantum gas reveals a stiffening of the excitation spectrum and a spreading of the dynamic structure factor across multiple branches. This antiroton effect contradicts the expected softening of the excitation spectrum due to dipolar interactions. The measured excitation frequencies for the lowest branch exhibit quantitative agreement with theoretical predictions, showing an increase in excitation energy with increasing dipolar interaction strength. Numerical analysis of the transverse behavior of the system reveals a marked change in the profile of the excitation modes at low and high energies. The density fluctuation profile, delta N, 2 for specific excitation modes in the lowest branch transitions from a Gaussian-like shape to a broadened multipeak structure with increasing energy. This change in shape leads to a drastic reduction of the strength of the dynamic structure factor of the lowest branch, causing higher branches to gain more relative weight due to the FSUM rule. The breakdown of the variational model, which assumes similar transverse structures for excitations and the condensate, is attributed to the change in shape of the excitation modes. Dipolar interactions exhibit momentum dependence, becoming attractive for small momenta and strongly repulsive for large momenta. This momentum dependence forces excitations to reduce their overlap with the condensate, transitioning from collective to single particle excitations as the excitation energy increases above the chemical potential. The observed stiffening of the excitation spectrum and the antiroton effect have significant implications for the behavior of the macrodroplet state. The increased stiffening is predicted to induce self-evaporation of excitations, prompting questions about interpreting finite temperature effects in such systems. The existence of a critical velocity and its relation to the incompressible nature of the droplet remains an open question. The results of this study open the path for further investigation into the excitations of the macrodroplet state and their impact on the system's behavior, particularly in the self-bound regime. The authors present a comprehensive list of findings from their research paper, delving into the intricacies of various methodologies and their implications. This summary aims to distill the essence of their work, focusing on key concepts, novel ideas, and significant discoveries. The paper commences by elucidating the importance of understanding the interplay between different variables in complex systems. It highlights the role of nonlinear dynamics, chaos theory, and fractal geometry in modeling these interactions. The authors emphasize the need for a multidisciplinary approach, combining insights from physics, biology, economics, and sociology to capture the richness of real-world phenomena. A pivotal aspect of the research involves the development of new mathematical tools and algorithms designed to analyze and predict the behavior of complex systems. These include advanced statistical techniques, machine learning algorithms, and network theory. The authors demonstrate how these tools can be applied to a wide range of fields, from financial markets to ecological communities, shedding light on patterns and trends that might otherwise remain hidden. One of the most intriguing aspects of the paper is its exploration of the concept of emergence. This refers to the phenomenon where individual components within a system give rise to collective behavior that cannot be predicted by examining the parts in isolation. The authors argue that understanding emergence is crucial for grasping the true nature of complex systems and developing effective strategies for managing them. The study also delves into the realm of chaos theory, illustrating how small changes in initial conditions can lead to drastically different outcomes. This sensitivity to initial conditions, known as the butterfly effect, underscores the inherent unpredictability of complex systems and challenges traditional notions of determinism. Furthermore, the paper touches upon the concept of self-organization, where systems spontaneously structure themselves without external direction. The authors contend that self-organization is a fundamental property of complex systems, driving the evolution of order and pattern in diverse contexts. In conclusion, the author's work offers a rich tapestry of insights into the nature of complex systems. By integrating ideas from multiple disciplines and developing innovative methodologies, they provide a framework for understanding and navigating the intricate web of interactions that shape our world. This research has far-reaching implications for fields such as systems biology, economics, and environmental science, among others, and serves as a testament to the power of interdisciplinary collaboration in advancing our knowledge of complex phenomena. Appendix A. Variational theory for a dipolar Bose-Einstein condensate in a tube-shaped potential. The variational theory for a dipolar Bose-Einstein condensate, BEC, in a tube-shaped potential is based on the decomposition of the 3D field into a product of a two-dimensional Gaussian function and a linear density along the axes. The energy per particle, given by equation A1, includes the single particle energy associated with transverse degrees of freedom, effective interaction, and a term describing the quantum fluctuations. The variational parameters are determined by minimizing this equation. The interaction potential is also derived, including its chi-dependence, which is essential for computing the lowest excitation band. Appendix B. Extended mean field theory for ground states of the dipolar BEC. The extended mean field theory used to model the ground states of the dipolar BEC describes two-body interactions through a potential that includes both short-ranged contact interactions and dipole-dipole interactions, DDIs. The extended Gross-Pitesky equation, EGPE, is employed to model the ground states, which includes the interaction potential and a term describing the quantum fluctuations. The EGPE is solved for a ground state of fixed linear density, and the quasi-particle excitations are found by solving the Baillie-Bode-Degenais equations. Appendix C. Experimental sequence for preparing and probing the dipolar BEC. The experimental sequence used to prepare and probe the dipolar BEC involves ramping down the magnetic field to rotate the polarization into the long axis of the trap, followed by ramping the magnetic field in the z direction to 0 to prevent high losses in the vicinity of the Feshbach resonance. Bragg spectroscopy is performed using a digital micromirror device to probe the prepared state. The experimental sequence is illustrated in Figure 5. The variational parameters, L, eta, are determined by minimizing equation A1, which is essential for computing the energy per particle and the interaction potential. The extended mean field theory is used to model the ground states, and the quasi-particle excitations are found by solving the Baillie-Bode-Degenais equations. The experimental sequence is designed to prepare and probe the dipolar BEC, and the results are presented in the main text. The experimental setup in this study includes a DMD, which can programmatically change the lattice by adjusting the relative distance between two gratings. The phase step d-phi is chosen to be small enough to avoid higher harmonics in the frequency, yet large enough to access high frequencies needed to resolve multiple excitation branches. The maximum excitation frequency is limited by the DMD's maximum refresh rate, resulting in a limit of 2.16 kHz. In the image analysis process, images are cropped to a region of interest and averaged to obtain the momentum distribution n, ky. This distribution is then used to calculate the mean momentum per particle, ky. In some cases, fitting a Gaussian to the excitations is not possible due to close proximity to the unperturbed cloud or distortions caused by collisions. Instead, ky is calculated numerically, relying on momentum conservation. Appendix E provides a comparison between the dynamic structure factor S, K, omega, and the observable ky. For short pulse durations and long excitation frequencies, the rate of change of momentum during a Bragg pulse can be related to the dynamic structure factor as given in equation E1. Assuming the initial position and momentum expectation values are 0, the observable Ky can be directly related to the DSF as shown in equation E2. However, the presence of multiple branches with comparable weight contributes to the imparted momentum, making it necessary to recast the integral in terms of the density of states. The fluctuation operator delta Nk is defined as the difference between the particle density operator psi x and its expectation value in the ground state, integrated over all space and Fourier transformed to momentum space. This operator is crucial for calculating the dynamic structure factor SO, K, omega, which characterizes the system's response to an external perturbation with wave vector k and frequency omega. In practice, the experimentally accessible structure factor S0, K, omega, is obtained by convolving SO, K, omega, with a sinc function, accounting for the Fourier broadening due to the finite duration of the Bragg pulse. Additionally, the actual energy probed by the experiment includes Doppler broadening, resulting from the motion of the atoms. This broadening can be quantified from the momentum width of the initial ground state and shot-o-shot fluctuations in the average momentum during the Bragg pulse. The total broadening due, KLL rho, is the quadrature sum of these individual mechanisms, dependent on the dimensionless wave vector KLL rho. For wave vectors Kyle rho equals 1, 2, the total broadening evaluates to do 1, 2 pi equals 75 Hz and do 2 pi equals 126 Hz, respectively. These calculations are essential for interpreting experimental results and understanding the limitations imposed by the experimental setup, particularly in regards to the effects of Fourier broadening and Doppler broadening on the measured structure factor.